Welcome to Summarize Science. Have you ever thought about creating a perfect digital copy of a video game world, one that an AI could use to predict the future flawlessly? That's the goal of world models, but they often fail spectacularly over long periods. A new paper proposes a fascinating solution, not by building a more complex prediction engine, but by teaching the AI a better understanding of simple geometry. The core problem is what researchers call representation quality. When an AI learns from pixels alone, it can get confused. Two different hallways that look identical might get jumbled together in its internal mental map. This graph shows the issue clearly. The blue dashed line represents a standard AI model, which quickly accumulates errors and goes off the rails. The black dotted line is a perfect oracle model that knows the true coordinates, showing what's theoretically possible. The researchers' solution is a technique they call Geometrically-Regularized World Models, or GRWM. The key idea is to enforce temporal slowness in the AI's learning process. In simple terms, this means that if you take a small step in the game world, the AI's internal representation of your position should also only change by a small amount. This forces the AI to learn a smooth, continuous map of the environment that mirrors the real thing. To test this, they used 3 different deterministic environments, 2 mazes of varying complexity, and a custom Minecraft world. In these tests, an AI agent would see the world from a first-person perspective, just like a player would. The goal was to see how long their new model, GRWM, could accurately predict future frames compared to standard models. The results are striking. Here, you can see a side-by-side comparison of a standard model, VAWM, and their GRWM model against the ground truth. The standard model gets lost quickly, teleporting to a visually similar pink wall or even hallucinating trees where a stone wall should be. In contrast, the GRWM model stays remarkably consistent with the actual trajectory, correctly tracking complex motion and objects. On an extremely long horizon test of 10,000 steps, the difference becomes even clearer. The standard model gets stuck in a loop, generating the same few frames over and over, failing to explore. But the GRWM model produces a coherent and diverse journey, successfully exploring different parts of the map because its internal understanding of the space is stable. This visualization reveals exactly why it works so well. Each colored dot represents a location in the game world, colored according to how the AI has categorized it in its mental map. The top row shows the standard model's map, which is a noisy, fragmented mess where distant locations are incorrectly grouped together. The bottom row shows the GRWM's map. It's clean, organized, and spatially coherent, almost perfectly mirroring the layout of the actual environment. So, let's recap the key points. The primary reason AI struggles with long-term prediction isn't necessarily its predictive logic, but its flawed internal representation of the world. By enforcing a simple geometric rule that consecutive states in the world must be consecutive in the AI's mental map, the model learns a vastly superior and more stable understanding of its environment. This leads to dramatically more accurate and reliable long-horizon predictions. This focus on representation could be a huge step forward for creating more robust AI for robotics, enabling agents to navigate our world, and for building the truly interactive and persistent digital worlds of the future.